So my name is Subodh Patil. I'm a theoretical physicist, and I will be joining the faculty at Leiden to research on the interface of cosmology and particle physics. Absolutely. So I'll be joining the cosmology group at the Lorentz Institute. I will be starting up my own group over time, but the groups themselves within the various members of the cosmology group, have very adjacent interests and work fairly closely with each other. I will be taking on PhD students and hiring postdoctoral researchers and trying to get external grants to bring more people, although I have worked very closely with Anna Achucaro in the past. And I look forward to working very closely with Alessandro Silvestri and Alexei Boyarsky and Konrad Schraun going forward, because as a theoretical physicist, my interests are broadly adjacent to a lot of different things. Cosmology as a subject is a fairly broad field. And some of the things I'm interested in interface anywhere from observations of galaxies from large-scale structure through to gravitational waves, through to the cosmic microwave background. And these are all things that the various researchers at the cosmology group have also worked on. So there will be a lot of interchange and exchange between us. Sure. So, just like when you look through a glass or you look through, a muddy pool of water, light travels differently in a medium than it does, let's say, in vacuum. And, the question arose at some point, now that we're in the era of gravitational wave astronomy, does that happen to gravitational waves? And the answer is, yes, it does. But the question is, how strong is that effect? And in what environments could that be in effect? Are we going to be looking at gravitational wave sources through the murky window that is the universe? And if so, how big is that effect? And that paper was focused on some claims that the effect could be quite strong. And what we understood was that actually that is not the case. However, in doing, at least for astrophysical gravitational waves, and by astrophysical gravitational waves, I mean those that are emitted by things that are happening in the universe, rather than, say, the Big Bang. But through the course of that study, we did understand actually what windows it might be possible for there to be some sort of a, if you like, an optical effect from intervening matter for gravitational waves. So that's something that I'm thinking about in the future, particularly with regards to these things called quasi-normal modes, which is basically how black holes ring down, and how these might be sensitive to an intervening environment, particularly as people look for the higher quasi-normal modes. That's something that I worked on a few years ago, and it's something that I'm interested in pursuing, definitely, in the coming years. Yes, and I think that the final answer is not very murky. The gravitational waves are a remarkably clean probe of the universe because they don't like to interact with things. Gravity is the weakest force out of all of them. So light is very easy to interrupt. If I put up a piece of paper between me and the camera, you can't see anything. But gravitational wave would go right through. But that can't be true. Absolutely, there is some residual effect, and it turns out that for primordial gravitational waves, those that come from the very, very early universe, which is something that we're hoping to measure with future experiments, there might be a chance that some of these may have a foreground, if you like, from the intervening large-scale structure of the universe. Absolutely. So the thing that sort of sets a cosmologist apart from the people that are thinking about gravitational waves today is frequencies. So the LIGO collaboration and the LIGO-Virgo collaboration is looking for gravitational waves of frequencies that come from things like black holes combining in the early in the late universe and neutron star mergers and so on and so forth. And these are relatively high frequency relative to the things that one expects from further back in time. So the types of things the types of experiments that would interface and give me information about gravitational wave signals of things that I'm interested in come from these things called pulsar timing arrays, which for instance, which are at this point detected through radio interferometer arrays. The square kilometer array, for example, LOFAR, for example, there's others. And looking further into the future, there is talk of maybe sending satellites, interferometer arrays into space that might be sensitive to these signals. LISA, for example, is something like having a LISA darted around the Earth-Sun orbit, which is at this point science fiction, but people dream of these things. And these things would give us actually a window onto gravitational waves generated at very close to the moment of the Big Bang, very low frequencies. Just like you have a optical relic from the Big Bang, which is the cosmic microwave background. This would be the analog of this for gravitational waves. It would be stretched, right? That would be stretched, but the cosmic microwave background has a thermal spectrum, so that has a very sharp peak that defines the temperature of the universe at any given moment, and that sort of redshifts over time. The gravitational waves from the early universe, if they come from a variety of stochastic sources, tend to have a flat scale invariant spectrum. So the frequencies are just as loud at any given frequency. So unless there's some interesting physical process that introduces the scale. And so the idea is to go looking for both, a primordial signal and for anything that might have happened in between. And exactly because this happened so far in the past, that signal, if it had a characteristic scale, gets redshifted more and more the further back you go. And so therefore you have to have a bigger and bigger instrument. Yeah, so pulsar timing arrays are sensitive to a frequency range that are, if you like, intermediate between very primordial signals and astrophysical. Yeah, so pulsars are some of the most regularly pulsing objects in the universe. I mean, their accuracy is up there with atomic clocks. And so the idea is if you have two pulsars in your field of view and they're sort of sending out a fixed signal with a definite time signature, and a gravitational wave sort of intervenes and goes past your field of view, there's going to be shifts in when you get those pulses from. And by looking at the changing in the timings of those pulses, you can infer that there was a gravitational wave that went by. Absolutely. And in fact, before LIGO had detected gravitational waves, people thought that maybe pulsar timing arrays would beat LIGO to being the first thing to detect gravitational waves. But in the end, it turned out to be LIGO. Yeah, so one of the things that I've worked on a lot and continue to work on recently, and it's actually a very, very technical, dry subject at the core, which is the effect of quantum corrections to phenomenon that happens in the very early universe. And it's a very, very technically elaborate subject. I needn't get into the details about that, but what the interesting consequences of it is the universe actually allows us, if we ever detect gravitational waves, it would allow us in principle to see the signature of fields that would otherwise not be talking to what we're made up of. So for instance, the idea is that the universe might be full of dark matter. I mean, we know it is full of dark matter. But all of the strategies we have to go looking for dark matter involves some very, very tiny, very weak interaction with what we are made up of. If that interaction is not there, then we still have gravity. Gravity is still, things are always going to interact gravitationally, but then we can almost forget about having a quote unquote direct detection. This paper was pointing out that if we live in a universe where there's lots and lots and lots of different hidden sectors, which a variety of models in string theory and beyond the standard model phenomenology say could be possible. It's another version of the multiverse, if you like. We live in just one of many different universes living one on top of another. The idea would be that we could actually be sensitive to that hidden matter through how it affects the correlation functions of primordial gravitational waves. So a hidden sector is something where it's just like you and me within a universe just like ours, but completely not talking to us. So it's as if dark matter, for instance, in our universe goes right through us, right? I mean, it's around us everywhere, but it goes right through us. We consider that to be a part of our sector right now because we feel it's gravity and it's really defining our cosmology. But the idea is, what if dark matter is exactly that? It's just another universe where there's other stuff that just doesn't talk to us at all, except gravitationally. In models of particle physics that go beyond what we call the current standard model, where people are trying to explain the funny numbers that we're seeing, they're very finely tuned numbers, and of course this begs the question, why are they the way they are? We find that there are these particular hierarchies that are very, very provocative, actually, to a theorist. They seem very unnatural from the perspective of someone just sitting in our universe. It feels like someone must have tuned them to be exactly that way. And so a very natural way to achieve these hierarchies, if you like, is to invoke that we are nothing special, we are just one of multiple different sectors, and that this hierarchy is a natural consequence of living in such a universe. Ordinarily, what an idea like that would do is just sort of takes a problem and puts it somewhere where it's hidden, and so you can't, you can't necessarily test it. And this paper that I worked on pointed out that that's not necessarily true. You always have gravity to answer to, and in particular, the quantum corrections, which were technically there was some difficulty in the literature to calculate them correctly. I would say we're the first group to actually, perform that calculation to the end and establish the precise nature of these quantum corrections. And this would allow us, in principle, if we had infinite sensitivity, which we don't, to our gravitational wave detectors at very, very, very low frequencies, we would be able to actually maybe even count the number of hidden sectors. They would do something to the stochastic noise in these gravitational waves that they wouldn't if they weren't there otherwise. And although it is, at this point, somehow in the realm of science fiction, I think part of the dialogue that happens between someone like myself, which is a theorist, and people that go observing things, is we have to give them reason to do the impossible. We have to give them motivation to, ask big questions. And so, the job of someone like myself is, even if it seems like it's so far out of reach out of our current technological abilities, it's to, just put the flag out there and say, go look for this. So unfortunately, I have a very boring answer to that question, in that I think when I was 6, I was one of these kids that really liked breaking open things to see what was inside of them. It really annoyed my parents, obviously. I think, my parents decided, okay, let's, instead of making him a vandal, let's, put science books around the house. And I think when I was very, very young, I knew that I wanted to be some sort of a scientist. I just thought it was really cool, what scientists did. I think when I was about 11 or 12, Stephen Hawking had just put out his book on the brief history of time, and there was a BBC Horizon documentary about it, and I saw it, and I just thought that was just so incredible that this is something human beings could do, and I really wanted to do it. And so for me, it was always just this sort of idealistic path that one could tread down. I'm very surprised that I'm still on it, to be honest, but it's something that I've always really, really been enchanted by and wanted to do. I feel very lucky that I'm still one of these people that, is on the path that they thought would be really cool as a kid and is still doing it. So in a past life, and still in a current life, I am an avid musician. I make electronic compositions. This has always been a big part of my life. A lot of my friends are musicians. I think it's actually quite common, maybe even something of a cliche among physicists to have a musical side interest. And I noticed the Epiphone guitar in the background there. And for me, it's something that I do. Sometimes quite seriously. I find it to be quite a relief from the day-to-day of my work, and it's just sort of another dimension of the human mind that I really enjoy existing in. The most amusing part about it is, for me, with my friends who are musicians, I find it extremely straightforward and easy to explain to them what I'm doing with my research, because they've all seen a Fourier transform and they all understand the principle of superposition very well. And this is actually something that makes communicating, concepts in physics quite simple. I find that people who have an appreciation of simple harmonic motion and what music is, and how it combines in different ways, are actually quite naturally potential budding physics amateurs. I've been looking for recommendations as to how to learn Dutch aside from Duolingo. I am starting to begin this process. Unfortunately, I have, between having done a postdoc in Germany in the past and now currently living in Denmark and now about to learn Dutch, there are 3 languages in the same foreign language department in the brain crowding each other out. So it's very, very difficult to learn. Yeah, I find it more difficult to learn languages very similar to a language you already know than something that's very, very distant. But I do find that Dutch is perhaps coming to me immediately at the beginning more naturally than Danish ever did. I think because, well, I'm not really sure why. I think, although the Dutch like to say that Dutch has a strange pronunciation or difficult pronunciation for foreigners, you should try come living in Denmark. It's much, much more challenging. I'm very much looking forward to it.